So today's activity is based on Hooke's law, which is the basic definition of simple harmonic motion, right? The force is proportional to the displacement. What we're going to do in today's activity is find the spring constant of a particular spring. So what would our problem be? Always phrased in the form of a question. What is the spring constant of a particular spring? How are we going to do that? We're going to take a set of masses, hook it onto the end of the spring that's hooked onto this little hook right here. We're going to keep adding masses to see what the displacement ends up being. So we're going to put a mass on, see what the displacement of the spring is, see how much it stretches. We're going to put another mass on, see how much it stretches, put another mass on, see how much it stretches, and so on and so on and so on. We're going to get at least 10 different trials of mass on the end of the spring and displacement of the spring, or the amount of stretching of the spring. I want you to take a closer look at the spring itself here, okay? This spring gets hooked onto the little hook that's at the top of this. The little ruler that's on the back of that may not be lined up with it. You can see in the one that I have in my hand right now, that's a bad example actually. The one that I have in my hand right now, the ruler on the back of it isn't lined up with the spring. You want it, when you start this activity, to be lined up with the spring. So how do we do that? Let's just squeeze the back and adjust it so that the bottom of the spring is at the 0 mark of the ruler. That's where we hook the mass sets onto, and that's where we're always going to measure the displacement from. So initially, the displacement will be 0, and as we add masses to it, presumably the displacement will be more. Maybe the spring is down here, or maybe it's down here. Read the value off of the ruler and record it. What's our data table going to look like? Well, of course, we've got to have a column for mass. I've only got 5 or 6 different spots to put mass in there. You're going to have 10, at least 10. And then you're going to have the same number of spots for the amount of displacement that occurs as a result of adding the mass on there. Now, mass and displacement themselves aren't going to get us the spring constant. We don't need mass and displacement. We need force and displacement. So where are we going to get force from? You got mass, you got displacement. Where are you going to get force from? What's the force that's causing all this to happen? What's the force that's causing the spring to stretch? What kind of force is it? Somebody whispered it, I think. Yep, Jessica? Gravity. So let's take that mass and let's multiply it by, well, let's first convert it to kilograms, and then let's multiply it by 9.81 to get the force. Just make sure that mass is in kilograms. Now that you've got force and displacement, you're going to plot a graph. The graph is always going to be y-axis versus x-axis, or second column versus first column. So it should look like this. Displacement on the y-axis and force on the x-axis. That graph should give you pretty close to a straight line. You should have Google Sheets plot for you a line of best fit, and you should have Google Sheets display the equation up here in the top right-hand corner. Y is equal to 0.34x plus 0.002, or whatever the case may be. Remember, this is the slope. That first number is the slope. But the slope is not the spring constant. We're close, but the slope is not the spring constant. How are we going to find it? I'm going to show you an analysis here that we do a lot in Physics 30, but only once or twice in Physics 20. I want you to look at this graph. Can you give me an equation from math class that describes that or any other straight line graph? Yep. Good. Y equals mx plus b. Okay, y equals mx plus b describes that graph or any other graph. That's a straight line, that is. Here's what I want to do. I want to replace the y-axis with the displacement. Now, this is a little bit confusing. I'm not replacing y-axis with x-axis. I'm replacing the y-axis with the displacement. It just so happens that the symbol for displacement is x, right? I'm going to replace the letter m, that's the slope, with the word slope. Why do I not want to leave it as m? Because I don't want to get it mixed up with mass. Okay, we don't want to confuse the slope with the mass. The x-axis is force, right? And b, the y-intercept, there shouldn't be a y-intercept here, or at least if there is, it should be very, very, very small. So it's essentially 0. So the equation for any straight line graph y equals mx plus b is tailored for this particular graph to look like this. X is equal to the slope times the force. Now what I want you to do is take an equation from your data sheet that has those two variables in it. F is equal to kx. I want you to rearrange it to solve for x, because that's what we solved for in our first equation. X is equal to F over K. Now what I want you to do is cross off things that appear in both of the equations. The equation that I got from my graph and the equation that I got from my data sheet. Cross off the x, the displacement, because it appears in both. Cross off the f, because it appears in both. What are we left with? In the equation for my graph, I've got the slope. In the equation for my data sheet, I've got 1 over k. So I'm going to say slope is equal to 1 over k. Or in other words, k, which is really what I'm looking for, because remember what my problem was. What is the spring constant for a particular spring? The value of k is going to be 1 over the slope. So plot the graph, make sure it's displacement versus force, not force versus displacement. Get the slope of it, flip over the slope, take the inverse of it, and that's going to give you the spring constant. Caitlin, is there a question there? No? Kenzie? It's okay to write down k is equal to 1 over slope. I'm just showing you where that comes from, because I don't want you to just say, oh, okay, I'll flip over the slope and get the spring constant. Okay, you don't have to write that out again. I've done it for you. But again, I want you to understand that it does come from something. It's not just something I made up. So there we go. Got our spring constant. What's our conclusion? The spring constant of this spring is blank, newtons per meter. Don't forget your units. I know this because, and then briefly describe the analysis that you did. The inverse of the slope of the graph of displacement versus force is that value. And then, of course, your sources of error. So what do you got to hand in for this thing? Got to hand in your problem. Let's go back to the start, actually. Got to hand in your problem, your variables. We talked about, not in so many words, but we talked about the manipulated variable and the responding variable, right? What are you changing? What changes because of what you change? And then, of course, the control variables all stay the same. There's one control variable that's critical. Hypothesis, you see that I've scratched out. I've scratched that out because if we're trying to find the value of a spring constant, it doesn't really make any sense to give me a hypothesis for that, right? Hypothesis in that case would be a complete and utter guess. You guys have no idea what the spring constant will be. So don't worry about a hypothesis. You do need materials, you need procedure, and then, of course, what we always do, data analysis, conclusion, and sources of error.